All right, so I dug into the archives and pulled up an old uh, engineering statics review packet that I made several years ago and got it out for you because I had somebody ask me about it. And I wasn't going to make a review packet, but then I thought, well, no harm. Oh, is that one on the website? That's right, there is. There already is one on the website. So now there's two. They're going to be a little bit duplicitous. Yes, because I'm sure I used one to make the other. So my guess would be that they have two pieces of information. But this one, as well as another one, are on the website. There's a few pieces that I want to highlight that I know we didn't cover. For instance, problem 269, where it says determine the magnitude and coordinate direction angles of the resultant force. We did not do coordinate direction angles in this go-round. So coordinate direction angles are, if you look at this F1 force down here, and you can see there's three angles from the positive, or from the X, Y, and Z axes. Those are called coordinate direction angles. It's just a different way of defining a vector in 3D space. But it's a way that I feel like I've never seen used in real life, so I decided to skip it this year. You should be able to analyze vectors like this one given here, which is, what do we call it? It's azimuth, and it's the azimuth angle and the other one. I can't remember what the other one's called at the moment, but we're given kind of the angle of the vector off of the XY plane. That's called the azimuth angle. And then some angle of where the projection of that vector lies in the XY plane. So in this case, to analyze this vector, all we need to do is say, oh, this is a 3, 4, 5 triangle. So that means 3/5 of it would be going up here, right? We could make a vector in the z direction that 3/5 of 125 is going to be 75 newtons. And then 4/5 lies in the XY plane, and that would be 100 newtons. And then to figure out how much lies in the X and the Y, we just have to say, well, in the X direction, we're going to have negative 100 cosine 20, and that actually would be positive. Sorry, I was thinking X was going this way. So it would be positive 100, you can't even read what that is, geez, cosine 20, right? So we're going to find the piece along the x-axis that's right here. And then in the y direction, we'd have our 100 sine 20. And in the z direction, we already know that it's 75 newtons. Yes. Y direction would be negative. Okay? Okay. So first page is just kind of resultant vectors, chapter 2 stuff. This should be like pretty straightforward for you. So let's flip through. I'll have you flip through the packet, and let's go through and circle the problems you'd like to see performed today. So I'll give you a minute to look at it. Again, if you're watching this at home, you can go download the packet off of the portal. It's under Resources and Handouts. I know there was a moment about a specified axis, so we'll look at 438. That's a moment about a specified axis problem. This looks like a simple machine. Here's a non-rectangular distributed load. I know that was one that people asked for. Here's another simple machine. Let's do this one because it's gross. It's a fingernail cutter. That'll be fine. Okay. This would be a good one to review. Right? Finding some unit vector stuff. Ooh, let's do this one down here. It isn't a triangle, you're right. I'm just a mean guy. Yep, after you get out of this class, you can view everything as a triangle if you want, but not before then. Hey, I think that's probably enough for today. We can come back and get anything that we've missed. So let's start with this moment about a specified axis. So the thing to remember when you're looking for the moment about a specified axis it looks like this. The moment about the axis is equal to I'm just using that as like the axis. So the moment about the axis is equal to the unit vector of the axis with a dot product of the moment, which is the cross product of a position vector from the axis to the line of action of the force. Okay, so maybe I should say LOA to F would be my subscript for R there, right? So R is the line of action to the force, crossed with the force, dotted with the unit vector of the axis. Okay? So here's a problem where this is a good one to start with. So we're given the force of 80 pounds. It's directed along the cable CD. Okay? In order to take the cross product of the force, what do I have to do? How do I have to define the force? Make it a vector, right? So right now I have a magnitude. I'm given the direction based on the geometry here, but I need to figure out what that actual vector would be. So I need to figure out what the unit vector of CD is. I'll do that first by figuring out what RCD is equal to. So in the x direction, it looks like from C lies on the y-axis and D lies 5 feet behind it. So that means I'm going to go -5 in the I-hat direction. In the J-hat direction, in Y, it looks like C is at 3 plus 4 cosine 45, and D is on the x-axis. So it looks to me like that would, and if I go from C to D, I'm going in the positive of 3 plus 4 cos 45, and that would all be in the j-hat direction. All right, can you see that? There's 3 feet here. This is 4 feet long, cosine 45. This length here would be 4 cos 45. And since we're starting at C and going to D, we're going from very negative to 0 on the y-axis, so that's a positive movement. And then in the Z, we start up at C and we end up down at D, so that means we're moving downwards. And D, it looks like, is on the XY plane, where C is 4 sine 45 above the XY plane. That'd be in the K-hat. So, at this point, how would you find the unit vector of that? Okay, Brendan says, I'd find the magnitude and divide by that. That's a totally reasonable approach. How I would recommend you find it is to go into your calculator and type unit V, -5, comma, 3 plus 4 cos 45, comma, -4 sine 45 like that, and it will give you the unit vector.
Also make the equation in TI-83.
Okay.
It does the same thing as A, B, C, and just put in those things.
Oh, cool. You can make an equation in the 83 that will do that? Yeah. Yeah, because you're just squaring them and dividing by the sum of the squares. Sure. Cool. So anybody get the unit vector for CD for me?
Negative 0.612, like how many units?
3. 3 would be good.
612 I hat, 0.712 j hat, and then negative 0.346 j hat.
All right. How does this help us again?
Like 611 for the x one. I hat, sorry.
Why is this important?
Let me know what direction.
Yeah, now we know that the force is going to be equal to 80 pounds times the unit vector CD. Oh, I'm sorry. I'm forgetting a crucial piece when putting this in your calculator. Square brackets. So people were saying that when they put this in their calculator, it says too many arguments, and that's right. You have to have square brackets around your vectors in TI calculators. Not sure why, but syntax, man. Computers ain't old stupid. But incredibly helpful. Has anyone been able to verify my Joseph's numbers here? Okay. So you should practice this because finding the unit vector on an exam, you're going to want to do it faster than you're currently doing it with me walking you through it, right? Okay. Okay. So if you multiply that by 80, what do you get, Joseph? 48, negative 48.9?
Yeah.
I hat?
56.9, well, 57.0 j hat.
Mm-hmm. Okay. So now we know the force vector from C to D. We're asked to find the moment that it causes about the axis that runs through the hinges at AB. Okay. So if we go back to, this is, where we started. Man, my page is looking Christmassy here. Right, this is where we started. We just found FCD. That's the F here. Now let's figure out what the R is that we need to do the cross product with. Anybody remember what choices we have in using R? Does it have to be perpendicular to the line of action? Yeah, it does not have to be perpendicular. It has to be from the line of action of the force to wherever we're taking the moment about. Right? So we're taking the moment about this axis. So what are some options we have? Yeah, so we could do, one choice would be for R, line of action to C, right, would be this vector here that goes up at 45. Excuse me? I'm pretty sure I could also do, and we'll have to try this, but I'm pretty sure I could also do a vector that goes straight from there over to D. Right? Let's try the cross product. So let's figure out what this vector here would be. I'm going to call this E. I don't think we have an E on here. So REC, we're going to go in the negative 0 in the x direction. We're going to go negative 4 cos 45 in the j direction. Doesn't matter if you're going from C to E or E to C. Yes, because we're the vector we're looking for here is the line of action. Yeah, I shouldn't have said line of action to F. That's kind of redundant. I should be saying from the axis to F, right? If you did it the opposite, you just get the opposite sign, right? But so, yes, we want to take the vector that goes from E to C, okay? Because so from the place we're rotating about to the line of action of the force. Okay. Now I'm proposing, I'm going to add another point F here that's on that axis, and I'm proposing that we could also use RFD, which would be 0I plus 3J plus 0K, and I think we would get the same value. Okay. Let's try it though. Let's make sure that this works. So we need to do the cross product. Again, if we were writing out the cross product, R cross F, did anyone evaluate what 4 cosine 45 is? Or could someone please? Okay, so this is 2.83, and this is 2.83. All right? So yes, Brandon, you definitely can put this in your calculator, and that is exactly what I would recommend you to do at this point on an exam, is to take the cross product in your calculator. If you're doing it by hand, we'd say I, J, K, 0, negative 2.83, negative 2.83, sorry, positive 2.83, and negative 48.9, 57, negative 27.6, right? So this is R cross F, where this is F, this is R. If you stick it in your calculator, you would do type in or find in the catalog cross P, and you would do square bracket 0, comma, negative 2.83, comma, 2.83, close the square bracket, comma, square bracket, negative 48.9, comma, 57, comma, negative 27.6, close square bracket, close parenthesis. And what do you get? Okay, so this is giving me the moment. Which one did you did this one? Okay, this is the moment about E of the force. Okay. Now let's do the moment about F of the force, right? Which is going to be RFD cross F. What does that give us? So we have to take the cross product of 0, 3, 0 and negative 48, 57, 26. Yeah, what's the answer you get? Yeah. Okay. And now, to complete it, we have to take the dot product with the unit vector of our axes. So what is the unit vector of our axes? We're trying to find the moment about this axis. I would say that the unit vector of our axes is negative I hat. Or we could say I hat, whichever one you want.
Why did we find the moment about E?
Because the first step in finding the moment about a specified axis is to find it about a point that's on that axis, right? And then we take the dot product with the unit vector, right? So now we're going to take the dot product with the unit vector. So I'm saying that the unit vector of the axes that I'm going to propose, so the axes is AB, and I'm saying that that unit vector is 1 I hat plus 0 j hat plus 0 k hat. Right? Because the axes is between A and B, right? So we don't move in Y, we don't move in Z, we only move in the along the x-axis. So now if I take that dot product, so let's do the unit vector dotted with the moment about E. That's going to be 1 times negative 83.2 plus 0 times this plus 0 times that. So it's going to be negative 83.2 I hat, right? Or it's just negative 83.2 because the dot product's a scalar, right? Then we do the same thing over here, the moment about the F. So we'll take the unit vector of the axes, dot it with the moment about the F, and we'll have 1 times negative 82.8, we get negative 82.8. 0 times 0, 0 times 146, okay? I would say that these answers are the same if we carried all of our values through, right? So there's something probably when we did the abbreviation here, we're dropping off some numbers, right? When we take 4 cosine 45 and 4 sine 45, we truncated it at 2.83. Whereas when we looked at the position vector over here, it was just 0, 0, or 0, 3, 0. Okay, so this one was exact, this one was approximate. So I would take this one as probably the more accurate answer. Why I did it this way is I wanted to show you that it really is, when you're looking for the moment about a specified axis, it's the R value that we use is any point on that axis to the line of action of the force. Any point at all. So we could have used a vector that went from A up to C and gotten the same answer. We could have used a vector that went from A to D or E to D, right? B to D, B to C. Any of those would be fine choices. Those would all give you different moments about those points, but if what you're ultimately after is the moment about a specified axis, it doesn't matter what point on the axis you choose, it's going to give you the moment. Okay? Questions on that? All right. Okay, let's go to our next. Ooh. Draw the shear and moment diagrams for this beam. What's the first step of drawing shear and moment diagrams? Finding the reactions, exactly, right? So we're going to have some reaction at A and some reaction at B. I'm going to call that the normal at A and the normal at B. This is a triangular load, so what does that tell us about the location of its resultant? 1/3, 2/3, so if it's 6 feet, it's 2/3 from the end, so it's 4. How do we find its magnitude, Liana? Yeah, find the area of the triangle here. So that would be 3 times 6, which is 18, divided by 2 because it's a triangle. So we've got 9 kip down here. How about the rectangle? 2 times 3 is 6. It'll be dead center. What's going to be the fastest way to figure out what NB is? Do I need to write all my equations? Just the moment, right? So at this point in the term, you should look at this and say, okay, I need to find NB. So I'm going to sum the moments about A and set them equal to 0. So it looks like we'd have 9 kip, 4 feet, negative direction, plus NB times 6 feet, minus 6 kip, times 3, or 6 plus 3, or 1.5 would be 7.5 feet, equals 0. So what do we get for NB? Nine times 4 is 36. 6 times 7.5 is 35. 37.5. So you're going to have negative 73-ish. Divide that by 6. You're going to have about 12. 13.5? That's about 12. Okay. So what does that tell us about NA? Yeah, so we know that we have 15 kip total and 13.5 here. We need one more. 2.5. I think 1.5. Yep. Okay. So to do that, what equation did I write in my head? Some of the forces in the y, right? What I'm saying is that I know NA plus NB minus 9 minus 6 needs to equal 0. Or NA plus NB equals 9 plus 6. Okay. All right. So now that we know this, NA 1.5, NB 13.5, let's jump to our shear diagram. What's the first thing we do? Jump up how much? We jump up to 1.5. Then what happens? Do we go horizontal over till we hit our 9 kip load and jump down 9? No. No, we do not. That is the resultant of the distributed load. So we look at the original load curve, which says we have a negative and increasingly negative slope, right, for a net negative change of 9, right? So we know the change in the shear diagram is the area underneath the load diagram. So in calculus terms, we'd say the change in V is equal to the area of Wx dx. Okay. So I know that as I go from 0 to 6 feet over here, I'm going to drop 9. Okay, so I start at 1.5. If I drop 9, I think that gets me negative 7.5, right? So I'm going to end up here. My slope starts flat because I start at 0 slope, and I go to a negative slope, increasingly negative. Then I jump up 13.5. So that would be, get me to 6. Then I go back to my load diagram and I look, I have a constant slope down. I have a total change of 6. Everybody feel okay with that?
How much, in terms of like how accurate do you want it to be, kind of with our numbers and like scale? Again?
How accurate do I want you to be with
Fine,
this?
just gonna show the
You
idea.
definitely need to know the value of these points. You need to be accurate in the sense of you know that this is concave down, and increasingly so, that it's a curve and it's concave down, and that this is going down, and that you end up on 0. That's the accuracy I'm looking for on this one. The problem actually comes in the next one, though, right? So the hard work starts right here when I say, okay, here's my moment diagram. Ah, bummer, dude. Right? We know that the slope of the moment diagram is the value of the shear diagram. So I start with a positive slope that's going to be flat right here. I guess maybe I should be doing this in red to stay consistent. Positive slope, flat. Then it goes negative. I know that I have a positive change. The location of this point here is the area underneath that. Well, shoot. I don't know what the area underneath that is, do I? Sure don't. So what am I going to have to do? I'm going to have to come back up here to this guy and to divide it into load regions and write some equations. Right? So, how many regions would you say I have, Daniel? You're fooling you say 4, which I know why, because you see the 9 and the 6, right? But these are the resultants of the actual distributed load, right? So we have an actual continuous load that goes from A to B. So we actually only have 2 regions, 1 here and 2 there. So what we need to do then is write our equation, or we could draw our free body diagram if you want for that first region. It looks something like this. And we know we're just interested in the moment, so we know there's a moment here. What's the value of this guy? How do we determine what the value of that triangle is? What's that? No, I don't need to make it a trapezoid yet because I know it starts at 0 right here. So how do I figure out what the value of this point is? Remember that this is x. Yeah, so the height of this changes with x, right? As you go across, like if I sliced it right here, I'd have one height. If I sliced it here, a different one. And if I sliced it there, a different one. So really, I need to figure out the slope of this line. Right? Which the slope of that line is I have 3 kip per foot over 6 feet. So I'm pretty sure the slope of this is 0.5 x. Right? Rise 3 over run 6. 3 over 6, 0.5. Okay. Where would my resultant of this little slice be? How far away, or how about this? Where do I want to sum the moments about? The cut. I always sum the moments about the cut. And so in a triangular distributed load, we know that this will always be 1/3 x. Okay. So let's do this. Sum of the moments about the cut has to be equal to 0. Counterclockwise is positive. So I'll have m plus, what would the magnitude of the resultant be? It'd be 0.5x, the height, times the length, x, divided by 2, because it's a triangle. So that looks like 0.5x squared over 2, or 0.25x squared. That's the force, times the distance it is away from the cut, 1/3 x, minus 1.5x. And this all equals 0. So the moment is equal to 0.25 over 3 x cubed negative plus 1.5 x. Does this jive with what we have going on? Let me zoom out a little bit so we can see our equations and that. Does this align with what I have drawn here? At 0, what value would we have? At 0, I'd have a value of 0, right? That's good. Okay. When would this equal, when would I end up with a, if I want to find out where this point is, how would I do that? This point where it becomes horizontal. Take the derivative and set it equal to what? Right? So this is the equation for a curve that I'm saying does this. And it's important that I know where this point is. Okay? How can I figure that out? Well, this is the equation of the line. So if I take the derivative of it, that would give me the slope. Right? Okay? So the slope of this is going to be negative 0.25 x squared plus 1.5, right? That's dm dx. So let's see when that equals 0. When x equals root 6. Okay. Let's see when x equals 6, where we're at. So let's put in 6 to our moment equation here. And what value does that give us for the moment? Negative 27? Okay. I'm sorry. Negative 9? Okay. How about so we know that here we're going to end up at negative 9. Where are we at when we're right here? At this point of inflection, what's our value? How can we find it? You plug root 6 back into your moment equation. And what's that give us? 2.4? Huh? 2.4? Okay. Now we don't have to write an equation for the second part, do we? Because we know we have a very positive slope that's decreasingly positive. The change we know is 6 times 3, right? So this has a height of 6, length of 3. The change in the moment diagram is going to be 6 times 3 divided by 2. 18 divided by 2 is 9. There we go. So we could have been sneaky and not done this by working backwards, saying, hey, I know how much positive change we have. I know I need to end up at 0. So that means I'm coming from a negative, and I have a positive change of 9. So I know that this point is at negative 9, right? So if I work from the right to this point, I could see I come up 9. So that means this is negative 9, and I could see, okay, that's what my graph looks like. What's that? That is a cheat code. Yeah, so you would still need to find this. Brendan has a good point. To make sure that the 2.45 is less than the negative 9. Absolute value less than. Okay. All right. You're going to say you can't call yourself a millionaire if you're $1 million in debt? Okay. Everybody got this? So let's go, while we're on this whole doohickey, let's go back here. Determine the equivalent resultant force and couple moment. Yeah.
How did you get the 5x times x in the very, for that moment?
Yeah, let's go back. So question is, on that last one we just did, how did I get which part? Right up here? This 0.5x. What I was doing here is finding the magnitude of this temporary resultant, right? So did you understand where the 0.5x came from?
That one is the slope.
Yeah, because so we need the slope of this line. If we're looking for the height of the line at the end, we need to know the slope of it as it goes across the whole region. So that's where I said, okay, it goes up 3 over 6 feet. So then that means that it has a slope of 0.5. So the value, or the height of my triangle is going to be 0.5x, right? So then to find the resultant, it's the area of the triangle, which would be the height, 0.5x, times the length, x, divided by 2, because it's a triangle. Does that make sense? Yeah. Okay. Ready? How do we find the resultant force of this here curve? Right, we're going to have some force right there, maybe. How do we find it? Okay, we need to find the area, right? So this resultant, okay, so we're going to go the integral of 1/3 x cubed from 0 to 3, which I'm pretty sure is 1/12 x to the 4th, 0 to 3, right? Personally, or like as an engineer? I don't know. Not super often. The question was, how often do you use calculus in real life? You know, most times I teach this class. Yeah, I use calculus most of the time. So what'd you get, Liana? So we got the resultant as 6.75 kilonewtons. Where is it located? Anybody remember how to find that? Did I?
You said we wouldn't have to do it because we'd always see it as a triangle.
Pull up the receipts.
Integral or the derivative?
I believe it's the integral of x wx dx over the integral of wx gives you x bar. Yep, it's the mean. It's kind of the centroid of the area. Let's see if this gives us a value that makes sense. So this would be the integral of 1/3 x to the 4th over, we already did this one, it's 6.75 from 0 to 3. So that'd be 1/15 x to the 5th right? Did I do that integral right? From 0 to 3 over 6.75. What's that give us for x bar? 2.4. What do you think? Reasonable? 2.4 from O? No, that's not where we are integrating from. We put 0 over here, right? So it's 2.4 from there. That's reasonable. So now to find the equivalent resultant force and couple moment at O, that's what we're essentially looking at then. Is a beam with a load of 6.75 located 0.6 away from the end, and we're asked to find OY, OX, and the moment at O. Yeah, so OX is pretty simple. So is OY, actually. 6.75. The moment at O, I'd like you to look at that. Don't write any equations and just tell me about what it is.
4.
Roughly 4. It's 0.6 times 6.75, right? Positive or negative? Negative. Negative 0.6 times 6.75. What did I do? What are we doing in our heads there? We're summing the moments about O. Okay. I think that's a reasonable thing to remember, yeah. You should know it coming out of this class. How to find the centroid of an area. Okay. So, I'd like to change this problem. I'd like you to draw the shear and moment diagrams for this beam. Okay? Draw the shear and moment diagrams for this beam. Is it really warm in here today?
Outside.
It feels pretty warm. So what do we immediately see when we look at this? Two sections. We also see immediately a triangle on top of a rectangle, right?
How would you find the slope of that line if you don't know how long the base is? Because,
You do.
but the height.
You do. So you know it starts at 2 and it goes to 4. So that means you have a change in height of 2 over a run of 3.
Right now, Brendan. Right now. Can you not sing this for like 5 minutes?
I like this problem as far as like, this is a good level of difficulty final shear moment diagram problem.
Have one resulting from the trapezoid thing, or can you see it?
Yeah, so the question is, could you have one resultant from the trapezoid thing? You could, you'd have to figure out where it is. So it's easier to say, I've got 1 2 kilonewton per meter rectangular load that's 6 long, right? So that'd be, what, 12 kilonewtons right smack dab in the middle, right? And that 12 kilonewtons is due to that rectangle. And then I have another load right here that's going to be 3 times 2 is 6. Divided by 2 is 3. A 3 kilonewton load that's 1 meter from the end. So what? So let's sum our moments about A. Negative 12 times 3 minus 3 times 5 plus by times 6 equals 0. So that's 36, and 15 would be 51 divided by 6. BY is 8.5. All right? So then that means AY, we have 15. So this would be 6.5. Okay? So I can draw my shear diagram. At A, I jump up 6.5. I have a constant negative slope, so I go in a straight line. So 2 times 3 is 6, so I'm going to go in a straight line down to a half. Okay? At which point my line is tangent and increasingly negative. Until I plunge down at the end. I guess I kind of did that a little far. I'm going to have negative 8.5 where I jump up. Anyone see clever tricks for doing the moment? I don't see any clever tricks. I mean, we can do the part up to the halfway point without an equation. Right? So it's going to be 6 times 3 divided by 2. So this is, again, kind of hard to see, but it's a trapezoid, so it's a triangle on top of a rectangle. So we know that we have a positive slope that's going to be almost flat when we get to right here. And when we get to right here, we know that the value of it is going to be the area underneath this curve. So that'd be 6 times 3 is 18 divided by 2, 9, plus 1/2 times 3, so 1.5, so 10.5. Right? Let me blow that up. So I'm going to make this part bigger. What we have there really looks like this. Right? Where this is 6.5, this is 1/2, and this is 3. So the area of this triangle would be 6, so that's 6.5 minus 1/2 times 3 divided by 2. So that has an area of 9. And then the area of this rectangle would be 3 times 1/2, which would be 1.5, for a total of 10.5. So we know our curve looks like that. Is 10.5 the maximum bending moment? No. Why not, Daniel? Exactly, because it's increasing for just a little bit past that point, right? We're still above the abscissa here, so we need to go over just a little bit to figure out where we'll hit 0. To do that, we're going to have to do some maths. They're not going to be fun maths. Okay? So let's draw the free body diagram, and yeah, I'm going to keep it from the right just because it's the way my brain works. It's boring, but it's my life. 6.5. Okay. So we know this has a magnitude of 2 kilonewtons. This is x. I suppose we can still divide this, make this a rectangle. We're looking for the resultant moment here. We know that if we treat these separately, that we'll have one resultant right here in the middle. Okay, that will be 2 kilonewtons times x. And that if we want the resultant of this guy, the height of it is going to be the slope here. We go up 2 as we go across 3. So the slope is 2/3 x. What's that? So let's see. A couple ways we could think about this. None of them are fun. It's 2/3 x, but starting at 3/. How am I going to do that? 2/3 x minus 3, right? Yeah. Two-thirds x minus 3. So that would tell me at, let's take 4, for instance, I'd have a height of 2/3 here. So this always tells me my height. Because at x equals 3, I have 0, right? Does this make sense, how I'm getting x minus 3? Okay, so that's the height. What will the length of it be? Right? So let's try our equation. If we sum the moments about the cut, set it equal to 0, counterclockwise is positive, I'll have minus 6.5 times x, right? That's the AY value, plus 2 kilonewtons times x over 2, right? This is the force, this is the distance of the resultant of the rectangular portion. Because it happens in the middle, right? Plus, now I need to figure out for the resultant of the triangle. The resultant of the triangle is going to be the area underneath the curve, which would be 2/3 x minus 3 squared divided by 2. That's the force. Where's it going to be? It's going to be at x minus 3 divided by 3. Right? Because x minus 3 is the bottom of this, and we know it's 1/3 of that. So x minus 3 over 1/3 would give me the distance to the cut.
So for this cut, we have 6.5 on the left side. Is that telling us how far along? Because we're zooming in on the section that's right next to the slope. Just wondering what that.
Yeah, so the question is, we're looking at region 2, right? We're writing this equation for this region, but we're still considering AY, the 6.5. Why are we doing that? Because what we're doing is, while we're looking at just this region, to cut it open and look at it, we have to look at everything to the left of the cut. Or we could do everything to the right of the cut and go this way. But I chose to do, we're going to start here and go all the way to there. Right? Great question. Lots of students stumble on this. You can't neglect what happens to the left of the region, right? Yes, we're looking at the internal forces here. You can't neglect the forces on the beam over here while you're looking at the internal forces in here. Okay? This is a big nasty. Don't you think? Look at that, Mama Jama. Okay? Yes, we do. Plus M, my bending moment. Right? So what should we do? Okay, we could simplify, I guess. That'd be fun. Okay, we could make our calculator take the derivative. But where do we know we're going to end up? We're going to end up back right here. The internal moment has to come to 0. So we know we're going to go up just a little bit more, and then we're going to come down. It's going to be a curve. So how do I figure out what this value is here? Yeah, we have to figure out what that point is. How do we figure out what that point is? We have to take the derivative of this and set it equal to 0. Good times. Correct. So we take the derivative of this, set it equal to 0, find what that value is, then substitute that value back into this, will tell us what the value of this is. Probably 6. Okay. I'm going to guess this is less than 11. Okay. You could do this though. It wouldn't be fun. No one would enjoy it unless you're sick in the head, right? But you could do this. If you get to a problem like this on the exam and you're like, oh geez, I have 5 minutes left and it's going to take me at least 10 minutes to distribute this properly, then to take the derivative and set it equal to 0, then to take that value and stick it back in. Here's what I recommend. Draw something that looks like that. Do what I just did. Say that's about 11. And you're going to get 9 out of 10 points. Then you need to solve it. Okay. All right. 10 minutes. So we got time for maybe one more. Which student's choice? What do you want to see? Frames and machines. You want to do the fingernail clipper? All right. The nail cutter consists of the handle and the 2 cutting blades. Assuming the blades are pin connected at B, pin connected, what does that tell us? They don't move, and vertical and horizontal reaction. Okay. And the surface at D is smooth. Ooh, what does that tell us? It can slide, no friction. Tells us something about the force that's happening there. It's normal. Okay. Determine the normal force on the fingernail when a force of 1 pound is applied to the handles as shown. The pin AC slides through a smooth hole at A and is attached to the bottom member at C. All right. Let's draw some free body diagrams. What do you say? Say, oh, Andy, that sounds like fun. I'd love to draw a free body diagram. Thanks for asking. Mm-hmm. Good job. That's D normal. And A normal. No. We're looking for the cutting force on the fingernail. A normal isn't what we're looking for. Okay. We are looking for, let's call it F normal. Fingernail normal. Why a fingernail clipper? Talk about a simple machine. To be fair, I didn't draw the fingernail. Okay, so I'm drawing the free body diagram now of the upper arm or knife. So what does that mean? What do I need to do with the D normal? It's opposite. Okay. And I'm going to throw on my BY here. Now let's draw the bottom. It says the pin, AC, is connected to the bottom piece. F normal is going to go the opposite way on the bottom piece, right? And AY be the opposite on this pin. Well, it says A to C is actually connected. It says AC slides through a smooth hole at A and is attached to the bottom member at C. So I'm making it one piece with the bottom. Okay. So, where should we start? Should we start on part 1, part 2, or part 3? Why should we start on part 1? Because we only have 2 unknowns, and we can solve for AY right off the bat, right? So let's do that. Let's sum the moments about D and set it equal to 0. Looks like I'll have 1 pound in the wrong direction. And D is 1.5 inches away. plus A normal, which is 0.25 inches away. That equals 0. So A normal is 6 pounds. Is that right? Okay. From there, I'm going to jump. I don't think so. I'm going to jump down to 3. And I'm going to sum my moments about B and set them equal to 0. Because I now know that A normal is 6 pounds here, right? So if I sum my moments about B, I have A normal be in the negative direction. Times its lever arm, which is 1.75, plus F normal, right, or finger normal, which has a distance of 2. So it looks to me like the normal force is going to be 5 1/4, 5 3/4. I mean 5 3/4. I don't know. 5 point what? 5.25. Where did I get 2 inches from? Going back up here shows that there's a 1/4 inch between the knife and here, right? Okay. Frames and machines. The key is breaking it into the right pieces, making sure that you draw in your free body diagram, if you put a force on one member going in one direction, on the next member where it interacts, it goes in the opposite direction. So D normal here I have going up on member 1. That means it's going down on member 2. It's equal and opposite. A normal on member 1 is going down, so that means it's going up on member 3. Okay?
So, just a quick question. So if it's like a connection point, say something's resting on Mars or whatever, and like on the last midterm we had like a ball point or whatever. So would you still flip the signs on that point, like flip the arrow direction?
So you're saying if we had like a problem like this, and there's a ball here, right? So maybe there's some weight here, 500 pounds or something. Would I flip the signs here? Yeah. Because, so if I was drawing this top, the free body diagram of this top piece, it might look like that, right? Then the free body diagram of the other piece might look like, right? So both these are flipped because they're going to be opposite. Does that make sense? Okay. So the question was, if you have a ball joint like this, would you still flip the sign? And the answer is yeah. In a framer machine, if you're drawing the free body diagram of something that the ball hits on one side and on the other, absolutely. Move that, flip them around. All right. A little over time. One topic that I note is notably absent from this packet is friction. right? So it's not in the review packet because we just did it. So I didn't think you'd need review on that, but if you do, go ahead and email me and we can do a friction problem on Friday. One more day.